Good afternoon and good evening, everybody. My name is Colton Marchessault. I am the Program Director for Vertical Flight Society Arizona, and you are tuning in to the NASA Aeronautics contributions to the Ingenuity Mars Helicopter presented by Susan Gorton in collaboration with VFS Arizona, Philadelphia, Redstone, and we actually have several other chapters in attendance, including the Hampton Roads chapter, some from San Jose and San Francisco. So welcome, everybody, and thank you very much for your attendance tonight. A quick reminder about mics and cameras. If you can see in the chat window, you should see that by default, everybody has their microphones and cameras turned off. This is so not to interrupt our presentation while Susan will be discussing her topic for today. Only other item I want to briefly go over is we will have a Q&A session at the end of Susan's presentation. At that time, I would remind everybody to please submit your questions at any point during the presentation. When we do get to that Q&A session, I will be proctoring those questions to Susan, and I will be asking them in the order that I have received them. Before we get into the presentation, though, I would like to give a couple of minutes to each of our chapter representatives to provide an update for their chapter. So we will start with the Philadelphia chapter representative, Stefano. If you would like to, please turn on your webcam and let's hear what you have.
Hi, Colton. Good evening, everyone. I'm Stefano. I'm representing for tonight the Philadelphia chapter of the Vertical Flight Society. I work myself in Leonardo here out in Philadelphia. And let me start with thank you, of course, all the officers and National for hosting and letting our chapter to be part of this meeting as well. For an update of the events that we have planned for this year, as you can see here, we have the 2021 Vehicle Management System Technical Meeting. It is scheduled right now for August 17th to 19th, of course, here in Philadelphia, and we are hoping to have this event in person. Philadelphia lifted the mask mandate last week, so of course, we are hoping to get better and better for that perspective. You can find more information on this link. You have to take note, of course, or if you go to the main page of the vtol.org, you will find on the left-hand side a column with all the events, and they're ordered by date, so it's very easy to find this one, and you can find more information. As for more events, we're of course planning more events throughout the year. Most of them possibly will be virtual, just to be sure that everyone feels safe until everyone feels safe to be in person. But of course, we're trying to smoothly transition back to the in-person meeting. That's pretty much everything from our chapter. Back to you, Colton. Thank you so much and enjoy the presentation.
All right, thank you, Stefano. Really appreciate it. We'll go ahead and turn it on over to the Redstone representative, Ed Martin. Ed, whenever you're ready.
All right, thank you, Colton. Good afternoon and good evening to everyone. So we've got just a couple of things coming up at the Redstone chapter that are planned. Coming up the week of August 10th, we're going to be having the Future Vertical Lift Cross-Functional Team Roadmap presentation by Brigadier General Walter Rugen, who is the director of the cross-functional team for FVL. It's going to be in person at the Radiance Technology Facility here in Huntsville, and then also offer virtual attendance for those who do not feel like they could attend in person, or for the rest of our audience from the other chapters. We're planning already our next technical meeting. We've been postponing those for quite a while because of the events. So late July, early August of next year, we're going to have a technical meeting on the development, qualification, and affordability of complex air vehicle systems. Again, that'll be in Huntsville, and it will be an in-person event. And then we're doing planning for the rest of the calendar year to have other events, and nothing to really announce at this point. And that's all I've got for you. Thank you, Colton.
Okay, thank you, Ed. Really appreciate it. And Chris, if you'll go to the next slide. So here's a little update from Mesa, Arizona. We are looking at continuing to have these virtual presentations. The collaboration between all the chapters has been amazing so far, and I think today's attendance will certainly be a testament to that. As we get into the rest of the year, our fall schedule is probably going to include some in-person events as well as virtual and potentially even hybrid. But of course, we just want to make sure that everybody's comfortable with any in-person events. And of course, we'll send out notices as those become available and as they are planned. A quick update from the STEM side of the Mesa, Arizona chapter. Our deputy and director are continuing to work with the ASU Polytechnic and MathWorks personnel to support a design, build, and fly drone effort. Hopefully, potentially, we're trying to turn this into a capstone project, but quite a bit of interesting things going on there. So if anybody has any interest in that, please feel free to reach out to myself. But with that, that's about the update from Mesa. So Chris, if you will, go ahead and go to the next slide. Unfortunately, we didn't have a chapter representative available today from Hampton Roads, so they sent us over a little snippet of what they have coming up. This is their call for presentations. In October, a 2-day conference is going on. Presentations are invited on the topics of structures, crashworthiness, and vulnerability reduction. Please take note of the email that is highlighted in blue within that text if you are interested. And please send your presentations over at your earliest convenience. Again, another amazing effort. Hopefully the rest of the year turns out smoothly there as well. So I think without further ado, we don't have any more chapter updates. So I think we're going to go ahead and introduce our speaker as soon as I get my connection working. Oh no. My apologies, I'm having some technical difficulties here with this one. Okay, there we are. So a little bit about our speaker really quickly. Susan Gorton has been working with NASA for 22 years and has been the NASA Revolutionary Vertical Lift Technology Project lead for the past 15 years. The project mission is to develop and validate tools, technologies, and concepts to overcome key barriers for vertical lift vehicles. Ms. Gorton is responsible for the work in this area that is conducted at NASA Ames, Armstrong, Glenn, and Langley. Ms. Gorton is an honorary fellow of the Vertical Flight Society, and we are elated to have her here today. So again, Susan, thank you for your time, and whenever you're ready, floor is yours.
All right, thank you. Thank you, Colton. And I want to thank the VFS, all the chapters, the Mesa, the Philadelphia, the Redstone chapters for inviting me to speak. I especially want to thank them for working together to make this easy for me to have a presentation that went out to a lot of folks all at the same time. So it's great. So welcome. Thank you for joining us. If you are not a member currently of the VFS, I highly encourage you to join. It's an amazing organization, a lot of excitement at the local chapters as well as national. So give it a look at vtol.org and see what we have to offer. So we'll go into what we're talking about tonight, which is the aeronautics contributions to the Ingenuity Mars Helicopter. So as a project mission directorate, and usually aeronautics and space don't usually cross paths a lot, but in this particular case, we did. The project with the Ingenuity Mars Helicopter get to Mars and make a historic flight. So let's talk a little bit about that journey. So first, I want to start off by saying, the Mars Helicopter team is a large team. It's comprised of 3 different NASA mission directorates: the Science Mission Directorate for the Mars Exploration Program, the Aeronautics Mission Directorate, which is where the project that I lead is, the Revolutionary Vertical Lift Technology Project, and the NASA Science Technology Mission Directorate. And the team was spread across multiple organizations. NASA JPL was the lead for this project, hands down, and supported by our work in aeronautics at NASA Ames and NASA Langley, as well as by our contractors who contributed so much to this: AeroVironment, Qualcomm, Solero, and others. So a big team spread out geographically came together to make this happen. Some folks said, hey, wow, this came up really fast. It kind of came out of nowhere, but I want to go back in time and tell you a little bit about the backstory. So in December of 2014, the JPL folks, the space side, said, we are able to show the feasibility of a helicopter lifting itself in a Mars atmosphere. And they were told at that time, hey, you should really connect up with the folks that do helicopter research on the aeronautics side of NASA. And so they came and they showed us what they had, and you can see our project engaged fairly quickly in January of 2015. And we saw what they had and saw how we could help them get to their goal and get to NASA's goal of having this concept fly on Mars. So we engaged right away, put a very small but focused team together. And over the next year and a half, we're able to then have a proof of concept, not just to show feasibility, but show proof of concept controlled flight demonstration. The controlled is a big word there. I'll show you that in a minute. This photograph down here is our initial team in our first meeting at NASA Ames in January 2015.
Uh-oh, I'm not entirely sure that that's just on my end. We seem to be having some technical difficulties. Please bear with us while we try to reconnect with Susan here.
Okay, I think I have audio, is that correct?
Yes, you do. We can hear you now.
All right, are you still seeing my screen?
We are, yep.
Okay, I'm going to keep the webcam off. I think we're having an issue with that, so.
Yeah, that would be fine. Thank you, Susan.
Okay. All right, so we talked about, we went from the proof of concept to the engineering development model in January of 2018, and this is where we really passed the test. Within NASA, anything that's proposed as a space flight or a space mission goes through a series of checks. You have to meet the gates, and there were gates put in front of this project that had to be met to show that we were confident we could do this on Mars. So we demonstrated that, and I'll show you some of that footage from January 2018. And so what happened then after we had that data in our hand, we were called what's baselined onto the Mars 2020 mission in May of 2018. Up until the point we were baselined onto that mission, we were not really allowed to talk about what we were doing. We couldn't discuss it out in public because it wasn't official that we were part of that mission. But once they announced that in May of 2018, then you saw a lot of things open up. You saw publications start to come out. You saw a lot of press release about that. And between that time of May of 2018 to February of 2019, that's when more improvements were made for the flight model for the Mars helicopter. Again, making things more robust, making sure that it was ready to survive the launch loads, the landing loads. And then from the point of 2019 to May, we were testing with the Mars rover, the helicopter delivery system. How do we have it right up on the rover? How does it be accommodated with space? How do you get it off the rover safely? And then after that point, it was on to support onto the Mars systems. So we launched in July of 2020. It's about a 7 or 8 month ride to go to Mars, and very successful launch and landing, as you know. So this is a video that just sort of shows the conceptual idea of what this helicopter demonstration was going to look like on Mars. So you see the rover drops off the helicopter and moves away. The helicopter does not go back to the rover. So that was the design, right, of the helicopter, was that it was designed to be a technology demonstration. So it was designed to just basically prove we could do this on Mars. It had to be capable of flight in a thin Mars atmosphere. The atmosphere is about 1% of the density of Earth. It's like flying at 100,000 feet. We chose, it was a coaxial design, partly because it was made it easier to accommodate on the rover in terms of folding into a small space, as well as the performance. The blades are about 4 feet diameter tip to tip. The mass 1.8 kilograms, about 4 pounds. That box, that's the fuselage, is about the size of a tissue box. It leaves the rover. It has to survive on its own. It has to repower and recharge its own batteries. It's solar powered. It was designed for up to 192nd flight per day. And I'm saying that was the design because later it showed we could fly it longer than that. The recharge time for the batteries is 1 to 2 sols. A sol is a Martian day. And that recharge time replenishes the batteries, because the batteries are discharged overnight to run the heaters to keep things warm, as well as during the flight time. Flight range was designed for up to 300 meters and heights up to 5 meters. It was designed to do autonomous flight and landing. We can't communicate to the helicopter during the flight. So commands are sent to through a series of networking to the rover. The rover transmits those instructions to the helicopter. And then we wait. And the helicopter is on its own to fly that mission. And then there's a delay in getting the return back to know if it really flew that mission or what happened. So it's truly operating autonomous mode on Mars. Again, it has to be able to survive those cold Martian nights. They get down to between minus 70 and minus 130 degrees. And again, as I said, it communicates via the rover. So it was designed to last for up to 5 flights. And that was the whole mission. Show us this can be done, so that it builds on the NASA philosophy that we used with the rovers, where we started off with a small Sojourner rover. And then as we demonstrated that technology, the rovers became bigger and bigger until now we have Perseverance on Mars, which is about the size of an SUV. So the helicopter itself has got several different kinds of features. The blades, they're made of carbon fiber with a foam core that are very lightweight and stiff. They spin at about 2,400 RPM. We have the radio antennas that talk to Earth via the rover. The solar panel keeps the battery charged, and you can see that some of the early animations have a round solar panel, but we ended up going with this rectangular shape. Inside this tissue box body has the avionics for the flight controls, as well as the heaters are inside the box that have to keep everything warm with insulation. There are sensors and cameras. There's a black and white camera for navigation. There's a color camera as well. The legs, the landing gear, are made of carbon fiber tubes, and you notice they've got this spring type arrangement at the top to give it some ability to flex during the landings. And then it is all battery powered. Now, this slide shows some of the evolution of the concept. So again, I said we started in 2014 with feasibility. Do we even think it can be done? And then 2016 with a proof of concept, where they start to see the rotor system is more mature. In 2017, we had the engineering model development, where again things are maturing, becoming more robust and more space-like. And then the 2019 flight model really shows the development in terms of of the control systems, but mostly the landing systems and some of the operational aspects. So I'm going to start by showing you a video of what the feasibility looked like. Now, this was just the folks from JPL brought this video, and they were rightly excited, saying this shows that a helicopter can lift itself on Mars. Now, it's lifting, and it's not shutting down because it's not lifting. It's shutting down because it won't stay stable. And this is in a Mars atmosphere. It's in a vacuum chamber, JPL. And you can see that they had some issues, especially right there at the end, right? So they showed us this video. And as I said, they're very excited. And we were excited too. But we said, we think that, we think you can do better. We think we can help you do better. Let's work on some of the issues that you're having. And so a year and a half later, then we had the 2016 proof of concept test. And again, this test is being run in the JPL 25-foot vacuum chamber. It's in a CO2 atmosphere and a very thin atmosphere, as would be on Mars. The issue with running in the vacuum chamber is that you can't simulate the gravity of Mars. But you can see we've got a much more stable system. It's still moving around a little bit. But it's definitely an improvement in terms of what we were expecting. Now, some of that movement is recirculation in the vacuum chamber. Some of it's a little unsteadiness. We also were powering this by a power cord coming up. It's not carrying its own weight of the battery. And again, this is because we had to show it's going to be able to lift itself on Mars, the Martian gravity, not the Earth gravity. So we were simulating the weight of the system on Mars. So there were quite a few different kind of tests that we were involved with in running. And as I said in the first one, the reason that it was not staying in the air was not it couldn't lift, it was because of the controls. And in the Martian thin density atmosphere, it doesn't get much aerodynamic damping. And so we had to do some real work in terms of what was the control system going to look like for the system, and to identify the control derivatives for the fixed system and some fixed system testing. Within the JPL vacuum chamber, we didn't really have a way to move a lot of air. So we put a robotic arm to look at how to develop the translational stability derivatives. We used a gimbal to develop the rotational stability derivatives. And then we did do some free flight and put what we called a wind wall, which were a series of fans inside this vacuum chamber to simulate some of the forward velocity. We did a lot of work looking at how those effects would, just the testing effects in that vacuum chamber would impact our results. But here you can see things on the fixed arm to start with. And then this is the rotating robotic arm to get the translational derivatives. And then we're doing some of the gimbal testing. Now I noticed how much the helicopter is moving there. And I'm pointing that out because on our 6th flight, we did have an anomaly happen, and the control system was robust enough to be able to withstand 20 degrees of oscillation. And you can see that's pretty much about what we had in that video. Times is the charm. Okay, so we've gone through the proof proof of concept test. Now we're ready to do the engineering development model testing in the Mars environment. And this was really the proof of the pudding test. This is where we were on track to meet the milestones. You can see the solar panels, the rectangular shape at this point. You see it's much more steady. Control system is keeping it much more steady. Move on from that one. So this was really our decision point that generated the decision in May of 2018 to baseline the Mars helicopter onto the rover and aboard the Mars 2020 mission. So we did launch, as I said, on July 30th, really successful launch. And in February, landed on Mars and start to get back some of the first images. And I'll go through a little bit as in some future slides here on how the helicopter gets off the rover and some of the first flight video and some other of these features. But this was just a compilation of some of my favorite shots. This was the helicopter still attached to the rover underneath it before it drops off. You've got the helicopter as the rover moves away from it. You've got the selfie that's in the bottom right of the rover with the helicopter in the background. In the middle is the helicopter after its first flight. And then on the far left is the image from the downward facing black and white camera of the first flight. And so what you're seeing is the shadow of the Mars helicopter on the surface of Mars. And you see the legs, and if you look in the corners up in the upper right corner, you can see the actual leg of the vehicle that's in the picture frame. So a really exciting time. So this is the video of the first flight. This first flight was pick up to a hover of 3 meters. It was a 33-second flight. We first knew that it had actually worked when we got the plot of the altimeter, and then we had to wait to see the video. So it's really nerve-wracking knowing that you had commanded something to happen and waiting to see if it really did. But this was a really exciting moment for the whole the Mars Perseverance as well as the Ingenuity team. So that was April 19th. That was the first flight. Short, sweet, but successful. So one of the things people commented was we didn't see any dust in that first flight, and JPL did some digital enhancement and of the first flight, and then you can see the dust kick up, and you can see the dust actually blowing away a little bit because there was a little bit of wind. There's a ghost image of the helicopter as an artifact of the digital enhancement. But there was dust. We haven't seen it be a problem for the helicopter, but they have seen the dust also during the forward flights of the vehicle. So in the initial concept of how things were going to work for the Mars helicopter, we thought there would be a takeoff and landing area, that the helicopter in a series of flights would go through the commanded sequence, take images, possibly find a new landing site. And it's very interesting that the artist's conception and what we thought was going to happen on Mars has actually happened during our time there. So as I said before, the helicopter was what we call a technology demonstrator. Its sole purpose was to show that we could fly on Mars. And so it had a list of milestones that are shown on the left. Survive the launch, the cruise, deployed it on the surface from the belly pan of the rover and unfold. Keep warm through the night. Charge from the solar panel. Confirm your communications. Spin up your blades and lift off. Fly autonomously, land successfully. So those were the milestones that were set out. And we expected to have 5 flights, over 30 souls. And then the plan was for the rover to move off. And the rover was going to then go about and do its primary science mission, because the technology would have been either demonstrated or had issues. Well, what actually has happened is really, again, it's exciting. We had the first flight on April 19th, then a second flight on the 22nd, and we went up to that 5 meter hover. On the 25th, did the third flight, and again up to a 5 meter hover. This time with 50 meters of lateral movement. On the 4th flight, and that one had sound recorded, which there are audio files on the mars.nasa.gov website. You can listen to what things sound like on Mars. On that flight, it went 117 seconds. So it was designed for 90 seconds, and we were pushing it by going to 117 seconds. But everything was operating really well. It had enough power. It had enough. It could charge. So they did push it. And on the 5th flight, they pushed it even further. They climbed to 10 meters. And they also went to a new landing site. So what had been decided then is that the rover was going to move to its new location. And they decided that the helicopter flights had been so successful that the helicopter would be allowed to sort of follow the rover. It has to stay close enough so that it can remain in contact. It also moved from being a technology demonstrator, because that job was done. We demonstrated that technology. It moved from being that technology demonstrator to being a demonstration of the operational companion and partner that an aerial vehicle can be to a rover. So at this point, it's going to operate and do some of those missions, like a scout mission or some geographical survey missions that could be part of a future helicopter or some type of aerial vehicle. So the 6th flight was 140 seconds. This is the flight where it did have a control system anomaly, because it lost a frame in the camera system, and that got everything with the timestamps messed up. And so there were some severe control oscillations, but it did land successfully, and only about 16 meters from where it was supposed to land. So that was actually very successful in terms of demonstrating that robustness of the control system. And then we did have a 7th flight on June 8th that took it to a 4th airfield. So it's going to track with the rover while that's an appropriate thing to do, and continue to work with the rover, but on a non-interference basis. So the rover's got its own science mission. It's got to dedicate priority to that. If you want to look and see where the rover and the helicopter are, you can go to a website, go.nasa.gov, where's Perseverance, and it gives you a map of, you know, where the rover has been and the helicopter and where they are now. There's a lot of information, a lot of the videos. There's blog files about the missions on the site mars.nasa.gov. So if you're interested in more about it, I encourage you to go to there. So we have been successful in flying the first flight on another planet and showing this demonstration. And the aeronautics contributions to this were done really in the early stages of the design. And then we handed it over to the space side to make sure that it would meet all the requirements for a space system. But some of the things that we were very involved with early on were the sizing and performance calculations with our sizing design code, and the NASA design analysis of rotorcraft. And it's now in use for future planetary area vehicles. We provided and advised and devised some testing methods and options for minimizing recirculation in the JPL vacuum chamber so that we get good information out of that system in that enclosed chamber. We contributed significantly to the control system design and the system identification, those parameters and how to operate. We had CFD, high fidelity CFD evaluations, first for running the airfoil performance calculations so that we could evaluate the performance, ensure that it would meet the goals. And then also later for some configuration evaluations, like the impact of changing that the solar panel shape. So I'm really proud to say that, you know, in this case, NASA Aeronautics and NASA Space worked really well together, and the researchers made significant contributions for the success of this helicopter. So some of that work, as I said, has been documented. You can read some papers on that. I have a list of those coming up in another slide of some of the publications that we did. But again, talking about what was it that the aeronautics was helping with, and again, it was in the early stages of how, you know, is the vehicle sized correctly? Will it have the performance that we think it should, that it needs to have? Will the flight control system be, you know, correct and able to autonomously fly? Will it be able to fix itself if we find out that when it first starts up that it needs to be a little more robust? How can we test in an enclosed environment in the JPL chamber? We looked at how to do some of these advanced testing methods like that rotating arm and the swinging arm. We did performance estimates with high fidelity CFD like overflow, and also with ROT CFD, kind of a mid fidelity code. And we used the 2D airfoil CFD so that we could come up with these the assessment of how these airfoils would perform. This is an odd environment because it is low Reynolds number and high Mach number. And so it's not something we have airfoil data to just go to airfoil tables. So this is a chart shows some of the numerical simulations that were done for the Mars helicopter in the Martian atmosphere. And in this case, they were looking at how that flow and the shape of the solar panel impacts with the body and the cube. You can see a very complex flow environment. A very different kind of application of some of our computational tools. But, you know, beyond aeromechanics, beyond the performance, right? It's not enough to just be able to fly a vehicle on Mars. You have to be able to survive the environment, the launch environment, the landing environment, the temperature cycles, And then are you accommodated onto the rover? How do you get off the rover and separate from it? What are the communications, the base station, and always, right, an emphasis on what is the power requirements you need, what is the weight, what is the space. So those are things that are beyond the aeromechanics. So if you look hard, this is the bottom of the rover. It's being prepared for launch. If you look hard, you can find the helicopter, but it's kind of hidden in there. There it is, all folded up into the smallest package that they could make so that it could come off the rover. The way it goes up is it's protected by this debris shield on the belly pan of the rover. And then the debris shield is dropped and the rover is released. So this is the demonstration of how that's going to work in the laboratory. And these are the kind of things that, you know, as aerodynamicists and dynamicists, we don't really think about. It's like, well, how am I going to fold it up and get it off the vehicle?
Yes. 2, 1, 0.
All right, so that was our test of that system, and it did work, and it worked on Mars as well. So we were really pleased about all of those different things coming together. I said I'd have a list of publications. You can see the list here. You can tell that some of these, you know, different conferences, different NASA reports, AIAA, some of the VFS reports, and some NASA contractor reports. So we have been documenting, we have been publishing what we can about this configuration. So just a summary, I want to leave you with the thoughts that NASA Aeronautics and the Revolutionary Vertical Lift Technology Project did provide helicopter expertise to the design development of Ingenuity. That research really came early in the design phase, and then the JPL contractor team continued that engineering development and all the accommodation and all the space flight testing for the Mars 2020 mission. And we're really excited about the success of this technology demonstrator because we've proven that you can do an aerial vehicle on another planet. And we now know that future planetary exploration will extend this concept and others to show that how this can be so successful. And just to wrap it up, I'll show finally kind of a movie that pulls it together that, you know, just shows the mission and some of the testing that was ongoing. All right. Well, I have enjoyed sharing this with you. As you can tell, we're really excited about the whole excitement about using an aerial vehicle on another planet, excitement about the Mars mission in general. So I'd be happy to take any questions if you have any.
Yeah, we actually have a couple of people who submitted questions, so I'll go ahead and ask those to you. I'm going to leave my webcam off, so I'm not just flipping them on and off. You're welcome to leave the slide up, Susan, or you're welcome to turn your webcam on, whatever you
I'll try. Okay, I'll try to turn my webcam on. See if we okay with that.
Okay. We'll see how it goes. We can always turn it off. Here's the hoping. All right. So we got a couple in here. The first one comes from Rick Derez. Could Ingenuity operate in Earth atmosphere at its higher pressure and density?
Well, so we made a accommodation on Ingenuity so that it could operate at the lower density. You would want to change the design if you were going to use it in the Earth environment. You know, it's spinning those rotors at 2,400 RPM, and you wouldn't need that on an Earth environment. So it could operate, but you really would want to design something for this environment.
Sure, I believe that makes sense. One quick reminder to everybody who's an attendee, if you do intend to submit a question, please type it into the questions window and submit them that way. If you have your hand raised, we unfortunately are not passing the microphone off to anybody, so please, if you have a question, submit through the questions or chat window. All right, so the first one was from Rick. Rick had a follow-up. Was the Martian atmosphere simulated solely by reducing pressure, or were any of the other fluid properties addressed?
So it was simulated by filling that chamber with CO2. So it was as close as we could get it to the Martian environment.
Okay. On to John Davis. For pitch and roll control, does it use basically conventional cyclic pick controls?
It does. It uses a cyclic and collective, on the bottom rotor, I think it only has collective on the top one. But that, yeah.
It's very interesting, actually. Okay, thank you. On to Robert Mormon. Do you believe that larger crewed helicopters can operate on Mars? And will any of the data help the flight to Saturn's largest moon, Titan?
So the information going to Titan it's definitely helpful. So what is helpful is that the helicopter on Mars performed like we thought it would, which means that we understand how to test and how to calculate and how to estimate performance in a different environment. So that gives us confidence in our tools and our preparation and our testing. So that is definitely a plus for any other exploration, even going to a different environment. The first part of that question was, what was that again, Colton? I'm sorry.
If I unmute myself, that might help. The first part of that question was, do you believe that larger crewed helicopters can operate on Mars?
So I think that we will see the growth in the helicopters, whether they'll be crewed or not, will be that might be a push. Right now, even some of the designs may change to larger payloads. And so what will happen is we'll have to take what are the requirements? What are the requirements for the next mission? If it's a requirement to carry a certain instrument, if it's a requirement to pick up samples, maybe it's a range requirement or an altitude requirement instead. What you have to look at, what are the requirements, and then see how your design can meet those requirements. So we haven't really talked about crewed helicopters. We're still looking at, when do humans get to Mars and how will they operate when they are there. We're looking at the helicopters or the aerial vehicles right now more as a partner, as something that's very utilitarian for the next missions, which will be robotic right now and then eventually humans.
Okay. Back over to Rick Derez. What was the most difficult technical challenge to solve in the Ingenuity design process?
Oh, you know, I don't think we can pick one, right? There's a lot of technical challenges to solve. You know, getting things to work in that very harsh environment, getting the communications to work, getting the navigation to work, and then just and making sure that it would be robust enough to live and survive on the way to Mars. So there's just a host of technical challenges, and I don't think you could pick out one. And that was the thing, is there were a lot that had to be solved in parallel.
Far too many to count. Can't imagine what travel loads are like that. From Stefano, how long does it take to send the information to the rover and receive the video back?
That depends on what the alignment is for the planets, but it's between it's between 13 to 20 minutes in terms of sending. But then, for example, the videos are going to take longer to offload and download from the helicopter to the rover, and then the rover to the orbiters, and then the orbiters through the interstellar systems. So, you know, sometimes we're waiting on the order of 3 hours, 4 hours before that data is transmitted.
Wow. I think that's quite a bit more than I was expecting.
Well, it's definitely not something that you're going to, you know, you can't fly this with a joystick, right? It has to be autonomous.
Right. Okay, thank you. Eric Coker, was there concern that the size of the solar panel would cause performance degradation?
Yes. So initially the solar panel was round, and then that was not providing enough power. And so they made the solar panel bigger, and then said, okay, now what effect is that going to have on the performance of the rotor system? Well, what is that going to have on the way that the rotor wake impinges on the fuselage, or any of the maybe directional stability derivatives? So that was part of why we did the CFD simulations, was to look at the impact of changing that solar panel shape on the wake and the performance.
Okay, next one is from Pedro Villanueva. What would be the best accomplishment that Ingenuity could achieve if it continues to work?
Well, you know, that's the thing, is it's been successful, more so than we probably thought at the beginning, right? We were biting our nails. You know, we did everything we could to make sure it would work, but you don't know it will until it does. And it did, and it kept working. And Mimi Ong, who's the JPL program manager, said, our helicopter loves Mars. And it said, because it's performing so well. So it's already done its main job. It's shown that this is possible, and it's captured the imagination of a lot of people too. And I think that's one of its main features, is the excitement that is generated around the country. I've gotten some, you know, hits from kind of around the world in terms of the excitement. So at this point, it's showing what can be done. It's showing how you can look ahead of the rover. So I think at this point going forward, one of the big things it can do is get an altitude perspective, so that the rover can make a better determination of where it's going. It doesn't have to go forward and then find out, oh, I can't go over that hill. Instead, the helicopter can look ahead and say, okay, you don't want to head towards that hill. You want to, you know, cut to the left and then go right. So I think there's that mapping, there's the observation, there's that guidance kind of scout feature that it could provide now. But I think there's all kinds of possibilities for the future in terms of what does the next vehicle do as a partner? Because, you know, once you've opened up that space, now people have confidence to work in that space, and I think we'll really see some interesting ideas come out.
Yeah, absolutely. Okay, thank you, Robert. I'm sorry, thank you, Pedro. Now over to Robert Kufeld. Can you talk more about the control system, such as how do you change torque for direction control?
Actually, I'm trying to think. I don't think I know the answer to that. So I will have to get back to you, Bob. So yeah, I don't really know.
Okay. Yeah, we'll write that one down, and I'll pass it along to you, and we'll make sure that we can get that one answered. Couple more here, and we do have about 4 more minutes, so we'll try to get as many of these answered as possible. Any leftover questions, we'll see if we can pull from the system and have those either answered offline or taken care of a different way. Over to George Stolb. What would happen if the solar panel was degraded by dust and a brownout?
So we were concerned about that, of how long would the helicopter be able to survive? Would it collect a lot of dust, and would that degrade the ability of the solar panel to run the heaters, right? Because if it doesn't have the heat overnight, then nothing's going to work the next day. So it won't survive a total brownout if the dust collects on the solar panel. Now that's one of the failure of the vehicle. It will fail at that point. However, what we've seen is that the dust is not really collecting on the solar panel. It appears to be not nearly what we thought it might be. So I think that there is some impact of the weight. We can see that in the calculations, kind of helping to clear things off. So, but if the dust collects on it, that will be one of the failure modes.
And so maybe a follow-up directly to that one, could it survive long enough to recover? Suppose that's subjective.
Well, right. It depends on how much was. If it was fully covered and couldn't charge, then it wouldn't, it would not survive. But right now, that's not been an issue.
Hope it doesn't become an issue. That would be ideal. All right, to our last question with a few comments. So from, I think it's Aaron Duda, does the solar panel efficiency affected by the dusty environment, or is the solar panel efficiency affected by the dusty environment in Mars? I think we're kind of talking about that right now. Is there any fault tolerant control or health monitoring system present?
Well, there are sensors that tell us that everything is functioning, and it goes through a checklist as we command it to, all right, get ready to fly. You're going to spin up, and there's a lot of checks it goes through. It says everything's functioning, everything's operational, all systems go kind of checklist. But there's not really I think what we in the helicopter world would say would be a health usage monitoring system, but more of a system check as the functional check as things are spinning up. In fact, it's during that process that they have what they call the watch timer fault. There's a timing sequence that has a probability of faulting, I think, once in every 7 times, and that fault is what delayed the initial flight. And but it doesn't do anything except everything shuts down into normal mode, and the next time they start up, that fault may or may not happen. So there's a known a fault there, but they thought the risk was greater to try to fix that fault than to just accept that it might happen once in a while.
Gotcha. Okay. Really interesting. So with regard, I think, to the question that was asked earlier about the control system and changing torque for direction control, we did have at least a comment submitted by one of our attendees who suggested it may be a differential collective. So if that is it, I hope that answers the question. I'm not entirely sure myself.
Well, that's probably the way it is, but I just don't know that for sure.
Sure. Okay. Well, that's actually all of the questions, and it looks like we're ending pretty much right on time. So I do want to take one quick minute. Again, thank you so much, Susan. Really appreciate your willingness to meet with the chapters today and all of our attendees. This has obviously caught the attention of so many different chapters, and like you said, international interest as well. So really appreciate your time for meeting with us today. For everybody who's attending, this presentation will be recorded, or rather has already been recorded, so you are more than welcome to watch after we get that all posted up on the VTOL webinar website. So with that, again, thank you, Susan. Really appreciate it.
Thank you.
Any final remarks?
Well, thanks very much for having me, and it's been fun talking to everybody, so thanks.
Excellent. All right, well, thank you, everybody. Have a great evening. We'll get everybody out here on time, and we'll see you for the next one.